In this particular lecture, let us start with pseudo random numbers. We have already seen that in order to carry out discrete event simulation, random numbers play a very important role, right? And all these experiments that we are generating the events with the help of random numbers, and therefore, it is very important that a generation of random numbers also follows a very good process. So, that is we are going to discuss in this particular lecture, that is about pseudo random numbers. So, first of all, what are pseudo random numbers? Simulation experiments require a source of randomness, right, and pseudo random numbers serve this purpose, right. First of all, these numbers are samples from uniformly distributed random variables between some specified interval, right. They have equal probability of occurrence as in the toss up of an unbiased coin. So, if we get a random number say between 0 and 1, something like 0.25. So, these 0.25 could have been, there are 2 digits here, 2 and 5. It could have been any digit between 0 to 9, all with equal probability. That is about 2 digit accuracy. We can have 3 digit, 4 digit, as many digit accuracy as the case may be. Is it all right? So, a random number generating scheme attempts to produce a sequence of numbers between 0 and 1, which simulates the ideal properties of uniform distribution and independence as close as possible, right. So, when you generate a particular random number, let us write down a random number arbitrarily. Supposing we have random number r .2457, right, 4 digit accuracy. So, this 0.2457, now you see there are 4 digits here, 2457. These 2457, first of all, each digit should be independently chosen. Suppose another random number R2 we get, and this R2 is, let us say arbitrarily 0.3769. So, you see these R1 and R2, these R1 and these R2, there should be absolutely no relation between them, right. That means, if the first number is 0.2457, second number need not be 0.3769, it could be any number. It could be any number, and in these 4 places there is equally likely that any number, any digit between 0 to 9 could have come, right. That is about that uniform distribution and independence that must be maintained about random numbers. But then we are using the word pseudo. So, why are we calling it pseudo? Basically, you see, the pseudo does not mean it is false. It does not mean that what we are getting out of the computers through the generator is something that is wrong or false. The fact is, it actually comes from a deterministic process, that is called a congruential generator, right. So, because it comes from a known process, a method. So, you see there is a issue there. What is that issue? Issue is that it comes from a particular thing, and there is something called a seed, a random number seed. So, supposing we give a particular seed, let us say arbitrarily, let us say a seed is say 1 2 12. So, as long as you provide the seed supposing we get a set of 10 random numbers, maybe I am just writing small random numbers. So, say 0.12, R2 equal to 0.37, R3 equal to 0.99, R4 equal to 0.72, R5 equal to 0.29, etc. So, you see as long as this particular seed 12 is given, same random numbers will be generated by the generator, because it comes from a deterministic process. It has got a both good thing and a bad thing. See, what is good thing? Good thing is that if suppose we have done an experiment and we want to reproduce that experiment, whether that in order to validate whether what we did is correct or wrong. The advantage part is, as long as we give this seed, we get the same random numbers once again. And the bad thing is that they are all predictable in a sense, because once a person knows seed, all the numbers will be exactly same, right. So, every time you do the experiment, you get exactly same results. What do we do to really create a replication? Because I said that replication means the random number experiment should be generated again. So, in order to get an replication, we must change the seed. So, this time we cannot use the same seed. So, not 12, we use suppose say 45. So, moment we use another seed, then we get a completely different set of random numbers, maybe r equal to 0.25, r2 equal to 0.72, r3 equal to 0.94, r4 equal to 0.46, etc., etc. So, you see we get another set of random numbers when we change the seed. Is it all right? Why this is happening? Why when we change the seed, we get exactly the same random number sequence, when we have a particular seed. It happens because they come from a deterministic process. What is that process? We shall see that now. So, that is why this is called a pseudo random number, right. But as far as the two properties, that the random numbers generated should be, number 1, uniformly distributed, and number 2, independent. They should be independent of one another, right. So, they are independent, they are also uniformly distributed. So, no issue there. So, these properties are fully satisfied and therefore, they can be used in experiments, no issue about that, but every time a seed is same random numbers will come out, right. That point must be remembered. Is it all right? So, sometimes really speaking, in order to generate truly random numbers which nobody can guess, the seed is also randomized, and that randomization process is not known to anyone. Is it all right? Suppose if you can relate it with your fingerprint. So, if you can relate it with your fingerprint, and since everybody's fingerprint is different, so as long as you will generate the same set of random numbers, right. These have very big bearing into things like encryption and maybe real world experiments. Anyhow, we will come to that later on. Here let us see how we actually generate a random number. One method could be linear congruential method of pseudo random number generation. So, you see there is a formula given here, x I plus 1 equal to a x I plus C mod m, where I equal to 0, 1, 2, right. So, this kind of generation of random number really follows these mathematical equation. What is that? X0 is a seed, A is called the constant multiplier, C is called the increment, and M is called the modulus. So, what exactly we do? We multiply the initial value, that is seed xi into A, I mean x0, that is the first number, multiplied by a constant multiplier, add a constant C or increment, and then take modulo m. Modulo m means divided by m and take the remainder, and therefore, you can understand that value will be always less than m, is it not? What should be the values of A, C, x0 and m? We shall discuss later, but first let us see what exactly this really does. So, if C is not equal to 0, then the method is called a mixed congruential method, right. So, what is a mixed congruential method? Where C has a distinct value and A and xi and m, they also have distinct values, right. That is called a mixed congruential method. When C equal to 0, then this form is called a multiplicative congruential method, right, because the formula simply becomes AXI mod m, is all right, AXI mod m. The selection of the values A, C, m and x0 drastically affects the statistical properties and the cycle length, and variations of the equations are quite common. So, lot of variations are actually available. Let us look at example of linear congruential method of pseudo random number generation. X0 equal to 27, A equal to 17, C equal to 43 and m equal to 100. So, this will generate, it is just an example, integer values will be generated will be all between 0 and 99. So, what is the first number? 27, because x0 is 27. Second number 17 multiplied by 27 plus 43 mod 100. So, it will become 502 mod 100. So, divide, remainder is 2. So, remainder, that will be the number. Third number 17 into 2 plus 43, mod 100. Why 2? Because last number was 2, and then 77 mod 100, we got 77. Next number 17 into 77 plus 43 mod 100, it will come to 52. So, 2, 77, 52, 3 numbers are generated, divide by 100, then we get 0.02, 0.77, 0.52. So, those will be our random numbers. So, you see, this is a deterministic process. Because it is a deterministic process, we call it pseudo random number, but all the random numbers that we generate, they are actually actual properties of the uniformly distributed and independence amongst each other. So, those properties are all satisfied. Now, multiplicative congruential method, as already discussed, that is xi plus 1 equal to AXI mod m, right, which is also rather popular. A is a constant multiplier, and this remainder is then set equal to the next pseudo random numbers. Process starts with an initial seed value x0. So, you see how this choice of m, x0 and A really comes in. M should be a very large number, because that is very important. Otherwise, you see, suppose m is small, like in our previous examples, that was, as I said, just an example. M should be very large. How much large? As large as possible. So, if it is a 32-bit computer, word length is allowed in a computer, then that number could be 2 to the power 31 minus 1 plus 1. That means large number of very large number of random numbers can be generated. Otherwise, what will happen? The sequence will be rather small. So, m should be very large. That is the first requirement. Second, the seed x0 must be relatively prime to m, right. As m is a power of 2, any odd positive integer for x0 would do. So, must remember that it should be relatively prime to m, and m is a power of 2. So, any odd positive integer for x0 would do, right. And the constant multiplier a should also be relatively prime to m, that is, it should also be an odd integer. A good choice of a is 8k plus minus 3. So, k you can put 1, 2, 3, 4, etc. Suppose you put k equal to 1, then a will be 11 or maybe 5, something like that. So, these are some choice of m, x0 and a, right. So, in order to test randomness of pseudo random numbers, what is very important is that the random variate is obtained by transformation of an uniform variate, and it is therefore necessary to test statistically whether the initial set of numbers are generated from a uniformly distributed number 0, 1. Actually, two things are here. The first thing that we have talked about here is called a random variate. You see, not all numbers are uniformly distributed. In our queuing example, please recall, we said that arrival is Poisson or service time is exponential. So, look here, if arrival is Poisson and random number you get is uniformly distributed, it will not do. If we take a random number and then we translate this to arrival, what will happen? You will be definitely getting a set of arrivals, and that will be random in a sense, but then they will be uniformly distributed, right. The events, all arrivals will be equally likely, but we do not want it. We want the arrival should be Poisson distributed, right. Distribution should be Poisson or service time should be exponential. How to do that? We have to convert the uniform distribution to a set of what is known as random variates. There are methods to do it, and we shall discuss at an appropriate time how to convert a particular number which may be uniformly distributed random numbers to a set of random variates which may be exponential distribution or maybe Poisson distribution or any other distribution like normal, Erlang, etc., etc., right. We shall discuss it at a later point of time, but even before that we should test statistically. It should be possible that the set of initial numbers which are generated, whether they are uniformly distributed or not, right. In order to have confidence in our experiment, that is also required sometimes, that the random numbers if that we are generating, whether those random numbers are truly uniformly distributed and they are independent of each other. So, that statistical test has to be done, and to really have confidence in the set of random numbers that we are making use of, right. If while generating random numbers certain problems of errors can occur, and these errors are usually departures from ideal randomness, all right. So, errors or departure from ideal randomness are all related to that generated number may not be uniformly distributed, right. The generated number may be discrete valued instead of continuous valued. See, sometimes they may be random, but certain numbers are not occurring, only a very set of discrete values are coming up like 0.2, 0.3, but 0.27, 0.29 they are not coming up. So, this could be a problem. The mean of the generated numbers are too high or too low, right. Suppose we have generated 100 numbers, right. Out of these 100 numbers, how many times the 2 should come, right. Suppose out of 100 numbers, 1 has come 20 times, 2 has come 10 times, 3 has come only 4 times. What will be their mean, right. So, you have to see the mean of the generated numbers should not be too high or too low. The variance of the generated numbers again should not be too high or too low, is it not? There may be cyclic variations such as autocorrelation between numbers. So, you see sometimes those numbers may be autocorrelated, even that is not good, right. Numbers successively higher or lower than the adjacent numbers, or several numbers above the mean followed by several numbers below the mean. All of these essentially tells that the random numbers that we have generated, they are not truly uniformly distributed if such departures from ideal randomness occurs. A good pseudo random number generator should avoid such departures from ideal randomness, and that is why we carry out some tests for randomness. So, in our next slide we shall see all these tests. So, apart from many tests that could be possible, some tests are discussed here. 4 of them are here in this page. The first one is called the frequency test. What is frequency test? The uniformity of digits generated are tested with the help of goodness of fit procedure such as the chi-square test or the Kolmogorov-Smirnov test, right. So, what we do? We try to find out that those the digits that we have generated, what is their frequency. The frequency test we will discuss a little more a little later. At this point, let us only know that we are trying to test the goodness of fit by looking into the uniformity of the numbers. The second one is called the gap test. These tests statistically analyze the number of digits that occur between the generation of a specified digit, right. So, let us look at what exactly it means. Let us say, suppose we have a set of random numbers. So, let us call some random numbers. So, you see 0.1254, 0.2379, 0.5165, 0.9299. Now, let us say okay, let us take another number 0.7652. Okay. Now, let us say we call a specified digit is 2, right. Let us call a specified digit is 2. Then you see how many digits are coming as a number between the specified digit. If we take them all as a continuous sequence, you see we get a 2 here, we get a 2 here, we get another 2 here, and we get another 2 here. So, between these two, how many digits? Number of digits in between. So, 2 digits 5 and 4. There is an occurrence of 2, there is another occurrence of 2. Between the two digits have occurred. In the next one, 1, 2, 3, 4, 5, 6, 7, 8, right. So, 8 digits have occurred between the next occurrence of 2, and then between the next occurrence of 2, 1, 2, 3, 4, 5. So, 5 digits. So, like this you form a sequence 2, 8, 5, etc., etc. So, what the gap test does, gap test really looks into that whether these number of digits that are occurring between the specified digit 2 like 2, 8, 5, etc., etc., whether these values are random themselves or there is a pattern. If there is a pattern, that means that numbers that we have got are not truly random. The next test is known as the run test. The runs test checks the sequence of digits that successively falls above or below 0.5 or checks to see if unusual runs up or down occurs in successive numbers, right. So, how many numbers are successively falling above or below 0.5, right. So, maybe you see if you look here, then there are two numbers that are falling below 0.5, then these numbers are all above 0.5. So, above 0.5 again 3. So, runs are first 2 then 3 etc., right. So, 2 numbers below 0.5, 3 numbers above 0.5. So, we can see that whether again these numbers are random themselves. The fourth test is called the poker test. The poker test, it examines individual digits to see if a single number or combination of numbers form pairs, threes etc., in successive set of 5 random numbers. So, whether a pair, so suppose we take a pair like 1 2, you see 1 2, if you take it as a pair, then you see a pair has come here, right. Now, is there this 1 2 again out of all these numbers? No, we have not found, but maybe if we take 1 2 for a large set of random numbers, how many times this 1 2 is coming, and these 1 2 is coming in successive set of 5 numbers. So, here is 1 2 3 4 5, in these 5 numbers there is 1 occurrence, in the next set of 5 numbers maybe there is 0 occurrence, in next set of 5 numbers again there may be 1 occurrence. So, you see 1 0 1 etc., that kind of sequence we shall get for a particular pair, and we have to see whether they are random in themselves or not, right. That is a poker test. The fourth one is a serial test, that this test checks randomness of successive numbers in a sequence. So, very simple. The product test checks for independence or correlation between sequences of random numbers, right. An autocorrelation test examines the autocorrelation patterns or relationships between numbers in sequence of random numbers, that is whether a number is dependent or another number in the sequence. Finally, the maximum test. The maximum test examines random number sequence to find out abnormally low or high numbers, right. So, frequency test, as we said, we will discuss a little bit more. It really tests how often number in a given range occurs in the sequence to ensure that the numbers are uniformly distributed. So, what you do? You keep a count of the different numbers that you have got. So, here suppose you have these 5 random number we have designed. So, we can check how many 0 1 2 3 4 5 6 7 8 9, right, how many are generated. So, you can see that out of all these numbers 0 is not there 0 times, 1 has come 1 2 times, 2 has come 1 2 3 4 times, right, and then 3 has come 1 time, 4 has come again 1 time. So, like this we have to make a note, 5 has come 1 2 3 4 times, right, 6 has come only 1 time, 7 has come 1 2 times, 8 has not there, is not there at all, and 9 is 1 2 3 4 times. So, you see, so these are the numbers, that many times these numbers are generated, and we have to see whether these numbers are random or not. Obviously, we should not do experiment with just 5 numbers, maybe we should take 100 numbers and then see how is this frequency of this 0 to 9 all these numbers, and we have to see whether by a chi-square test or a Kolmogorov-Smirnov test, whether goodness of fit really results, right, and the pseudo random numbers must pass the frequency test among others, right. So, so far we have discussed how to generate random numbers, the scheme of discrete event simulation scheme, some examples of how to have pi of Monte Carlo simulation. In our next classes, we shall see more of you know what is known as how to generate random variates and some giving examples, right. So, thank you very much.